Welcome back. So with the notion of an n-dimensional one surface of some smoothness class, now we are going to put that assumption on the boundary of our domain and state and try to prove an extension results. Okay, and remember, extension results are very important in obtaining density results, and so density so if you approximate general functions in a sublaw class by smooth functions, then that will help us in obtaining good estimates. Okay, so let me state the theorem. So this is the extension theorem. So remember, we have already obtained extension theorems for some specific domains. So suppose omega tilde are bounded domains such that the boundary del omega, so this is an n-dimensional n-1 dimensional surface is of class Cm. And remember, m is at least 1. So this means that this boundary del omega can be written as union of finite union of simple pieces, and this omega sits in rather omega bar. So okay, so then we have then given any f in the sublaw class Hm omega. So this m and m are same. So if just want H1, then C1 will do. Okay, so this m and m are the same. Given any Hm, there is an extension f of f, little f, such that f is in Hm omega tilde, and for us more importantly estimates. So this f we should have control. So this Hm omega tilde less than constant Hm omega. So this constant of course does not depend on a particular function, it depends only on the domains omega tilde and other things, but not on the function. That's important. Okay. The same extension result also holds, no, not same. So we also have an extension result. Result when f is smooth function. Okay, so given small f in this class, there is an extension big F which is in the class Cm of omega tilde bar. Okay, in either case, either the smooth case or the non-smooth case. So this extension F has compact support in omega tilde. And as we already seen, that helps us in obtaining density results. So since F has compact support, we can take its modifiers, and those modifiers will approximate our little f. That we will see next. Okay. So this is the extension result. So this is for a general domain, and we are putting this hypothesis on the smoothness of the boundary. Okay. Okay. So proof, this is only a sketch. So you have to fill in all the details here. So I will just recall. So in a previous class, under an assumption, let me just recall that. This in fact we proved it in detail. This is the theorem. With this assumption, so if for every point on the boundary, if we have an extension of the given f into a small ball around that point with this estimate, then we obtained an extension of f in the whole domain. Okay. So now we have to just verify this hypothesis is satisfied from the condition we have imposed on the boundary. Okay, so let me just write that. So that is the theorem I am referring. Okay, fine. Okay, so it suffices to. So once we understand what to be done, it suffices to show. So I just concentrate on the Sobolev class, so you can do the same thing for the smooth class. So there is no trouble at all. It suffices to show that for each point on the boundary, j on boundary, there is a function f j in Hm, a small ball, okay, around that. So for some r positive, such that, so this is an extension of f in the ball. So f j of x is equal to f of x for x in omega intersection bj r, and this fj, the Sobolev norm, is controlled by F. Okay. So, if we can show this one, then we can apply the previous result and obtain by using partition of unity an extension of little f to the. So, in this case we obtained actually, okay, this implies f has an extension in this, we call it omega rho. So, that is rho neighborhood of omega for any rho So, if this condition is satisfied, then we obtain an extension in this rho neighborhood of omega. So, in the present context, we have to only take in the present context so we have to only pick this rho present context, pick rho positive such that rho is less than distance between the two boundaries del omega and del omega tilde. Okay. And then we will get an extension in omega tilde. In fact, this omega rho now will sit in omega tilde. Okay. So, how this is done? That is where we use the hypothesis that the boundary is of class CM. So, here we use the hypothesis del omega is of class CM. And we also use the extension theorems we have already done for rectangular parallelepiped and cube. Okay. So, let J in del omega. So, let me draw some picture. So, what we are doing will become clear. Okay. So, this is del omega. So, let me use different pen here. So, here is J, okay, and small neighborhood. Okay. 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 So, since this del omega is a surface of class CM, we can find a neighborhood. I will call it Uj of J such that this piece sitting in Uj, okay, is given by the equation xn equal to phi x prime. So, x prime is again in some d. So, this is the projection of del omega uj onto xn equal to 0. So, since del omega is union of simple pieces and j is a point on del omega, such a thing can always be done. So, here I am just for the ease of writing choosing xn. Okay. So, this need not be an xn. So, it could be any coordinate, okay, just for the ease of writing. So, I am doing that. Okay. So, we may also assume, so again this is for convenience, we may also assume that xn is bigger than phi in omega intersection uj. Otherwise, you change phi to minus phi, that is all. Okay. So, this portion, this shaded region is xn bigger than phi. Okay. And now you use change of variables. So, let me just consider the change of variables. X going to y. Okay. So, so again let me draw the picture. So, it will be so this is going into, this is x space, x variables. So, I am just writing in y variables. So, this is y. So, this is 0, this is yn equal to 0. Okay. So, j is mapped onto 0. So, what is y? So, yi is xi minus ji. So, this is for I equal to 1 to n minus 1, and yn I am just writing xn minus phi of x prime. Okay. So, x prime again, just remember that. So, by the assumption on phi, phi is of class Cm. So, at least C1 is there. So, this is a smooth change of coordinates, and inversion is also easy to write. Okay. So, and this shaded region goes into, so if we can also, it goes into something like here. So, let me just write, okay, that it comes here. Okay. So, by choosing smaller radius if needed, so we can assume that there is a cube here. So, this is, I call it Ka plus. Okay. We can still consider the smaller one. Okay. And so, we already listed some properties of these functions in Sobolev class. So, under change of variables, that smoothness is again So and consider new function and consider small z. So y, this is f of let me just y1 plus j1. So in fact we are already using the inverse transform. This is yn plus, so I should write again phi in terms of this y1 plus j1 etc. Okay, and this z, small z, belongs to hm ka plus for some a positive. So in fact we are considering a smaller domain here, though this mapping will so this omega goes here. Okay, so this is the under this, so since we are assuming xn is bigger than phi, so this is yn positive, right. So this portion of omega is sitting here in yn positive. But for such a function we have already obtained an extension into the whole cube. Okay, so that's let me just write that. Okay, so this is k minus. So we have already seen how to obtain an extension to the whole of Q Ka. Okay, and with necessary bounds, that's important. Okay. Okay. But there is an extension so let me write capital Z of y of little z to Ka with necessary bounds. Okay, so let me not write it here. Okay, and now what we have to do is only pull this extension. Okay, so now we have an extension here, call it z. So here it is z, and now we have this entire thing capital Z, and now we just pull back, go back from here to here. Okay, so let me just write that thing. Okay. Okay. From Z using the inverse transform, we obtain the required extension. So let me just write that extension F in B gyro R for some R positive. Okay, so let me not write everything in detail, and then you apply a previous theorem and obtain the extension of f into omega tilde. Okay. So, just so our next task, remember our aim is to, okay, so let me just, so details, okay, fill in the details. Okay, few comments before we proceed further. So, here we obtained an extension result by putting some smoothness condition on the boundary, and in the literature you find many assumptions on the boundary depending on the context. Okay, there are external sphere conditions, internal sphere condition, external cone condition. Okay, so those assumptions are generally used for extension result like this we have done here, and this hypothesis on boundary become crucial in obtaining regularity estimates, especially for the elliptic boundary value problem near the boundary. So, in the domain there is no problem, but when we want to get regularity estimates near the boundary, obviously we have to put some conditions on the boundary so that we have the required regularity. Okay, so they are hard estimates, generally they are very hard estimates, and one has to, depending on the context, may change the smoothness assumption on the boundary. Okay, so with for our purposes, and this assumption on the boundary that is of class CM, it includes many domains of interest like sphere, ellipse, cone, cylinder, and union of intersection of two balls, all those things. Okay, so this assumption covers a large number of interesting domains. Okay, so remember our aim, so that's our next goal. Okay, so this integration by parts you, so just remaining few minutes, I will just recall that, and again we will continue in the next class. So, this u v nu I, this is ds minus v du by dxi. Okay. So, this is integration on the surface del omega. So, these are domain integrals. So, certainly this is valid. So, that is the classical result. So, if u and v are c1 omega closer, so they have continuous, both u and derivative have continuous extension up to the boundary. So, we would like to deduce this one also for u v in h1 omega, and this one is repeatedly used in studying elliptic equations. Okay. So, for that we first obtain the density result that C1 omega bar is dense in H1 omega. So then we can approximate U and V by a sequence of smooth functions. So this density result is just corollary of this extension result. Okay, so that's now it's not a big problem. So density result is immediately obtained. The only trouble is we have to give meaning to this UV on the boundary for UV in H1 omega, and that leads us to the notion of trace. Okay, so once we develop that notion of trace, so that's essentially defining U and V in appropriate way on the domain on the boundary del omega, and that will do the job. Okay, so that will take up in the next class. Thank you.